Hello everybody and welcome to the second video lecture for SEM1, Confirmatory Vector Analysis. In this video lecture I want to give a summary of the first lecture. So in the first lecture we see that we have this general vector analysis framework. What we do in this framework is we want to measure a set of latent variables, eta, this is a vector, say of the latent variables of person I. So say my level of neuroticism, of extroversion, of agreeableness. And we assume that this is linearly reflected on a set of observed variables in y. So say my answers to the questions, do you like to go to parties, are you nervous, etc. It's a linear function of so y is a linear function with lambda, the vector Long's matrix, times my latent scores plus a vector of residuals, so epsilon of I, so my residuals or my measurement error. Now we assume all these vectors are normally distributed. So here I say y, and y now no longer has the subscript I to indicate that this is from a random person. So my responses are not random because I just gave the response, say 4, 5, 3. And that's it. But from a random person, another person might have said 2 or 5 or 1. So over people, this score vector has a distribution. So I assume that the full set of responses is normally distributed, multivariate normally distributed, with a mean factor of 0 and a variance covariance matrix of sigma. Now this mean factor of 0 indicates that we can quite arbitrarily take out the mean of our variables and center them. We could also put a mean factor in here called mu, but then we need to estimate that. And it turns out we have, say, if I have 10 indicators, we have 10 means. 10 means we want to estimate, so it's the same. So it sort of cancels out. So until week 3, we will ignore this. And we'll simply say, let's say it's 0, because we only care about the variance structure. In week 3, when we have multiple groups, this will become important again. Eta is also normally distributed with a mean of 0 and a variance covariance structure of psi. Now this mean of 0 is because we needed to scale eta. It has no unit. It could be a mean of 0, could be a mean of 100, could be a mean of 1000, and we need to set that somewhere. In IQ test it's typically set to 100, for example. But we will say to set it to 0. Psi is the variance covariance matrix of the latent variables. Epsilon has a normal distribution of 0, and now the 0 is important because it's error, so it should not have a structured error, so this is always 0. And it has a variance covariance structure of theta. Now, these matrices, lambda, psi, and theta, are all you need for the confirmatory vector analysis model, and they will form the model. In structural equation modeling 2, I will explain the covariance algebra to derive the expected variance covariance structure of this expression and more. And here I will just give it. That is this big expression here. Now this is very important. If you understand this expression, or not really understand where it comes from, but rather if you can fill it in and get the sigma, you pretty much understand confirmatory vector analysis, and this is pretty much all we do. This tells me that my model implies a certain variance covariance structure, sigma, and that equals lambda, the vector Long's matrix, times, and this is matrix multiplication, the transpose of lambda, psi first, times the transpose of lambda plus theta. This means that for these matrices we can form an expected variance covariance structure. Now what we will do is we will then try to find elements of these matrices that lead to a sigma that closely resembles our observed variance covariance matrix S. A bit more technical on how we do that is we do that by minimizing this expression. This is not something you need to do. You don't actually need to form this expression as well. But under the hood of any software that does confirmatory factor analysis is this expression first, that forms sigma, and then this expression in some optimizer. This expression is proportional to the log likelihood ratio. So if you want to go into detail and see where this comes from, I think this is minus 2 over n times the log likelihood, how likely your data is given your parameters, minus how likely your data is given your parameters in a model that's in which sigma equals s. We will see that if sigma equals s, so we have a perfect or saturated model, this expression becomes 0. So then s times s inverse is an identity matrix. Trace, which is the sum of diagonal elements of a matrix, will then equal the number of variables minus the log determinant. So s times sigma inverse would then be an identity matrix again. The determinant of an identity matrix is 1, the log of 1 is 0, so this is minus 0. Minus p is the number of variables, so then we would get 0. If our sigma is not equal to s, we get something higher than 0. So the lower this function is, the better, because the better our sigma resembles our s. This is called maximum likelihood estimation. You might have heard of that term before. And maximum likelihood estimation is a general way of optimizing a model to get parameters under which our data was as likely as possible. So say I have a coin, I throw 50 times head, 50 times tails. I want to estimate the probability of throwing heads. Then that probability, the data was very likely if the probability is 0.50. But very unlikely if I only had a 10% probability of throwing tails. So you'd say it's 0.50. That's the principle of maximum likelihood estimation. Now in confirmatory factor analysis there are two main rules for identification. We need our model to identify it in order to be able to estimate it. The first one is that the scale of the latent variable is unknown. That means that say we measure temperature, but real temperature doesn't really have a unit. So we could measure it in Celsius, but we could also measure it in Fahrenheit or Kelvin or any other scale we can come up with. So in our model we need to fix the scaling. We need to fix a mean, but we already did that. We said mean is 0. That's not that important now. What's more important is that we also need to fix the variance. We can do that by simply saying this model has a variance of 1, this latent variable. Or we can say this latent variable has a similar variance to the first indicator. And that's by setting the first factor loading to 1. So simply said, for every factor, we either need to set the variance of the factor to 1 or the factor loading of the first indicator to 1. Now there's some considerations. In the case of setting the variance to 1, the factor loadings could be positive or negative, so that means we could have neuroticism but also emotional stability. If you set the factor loadings to 1, then we could have the case where we set the factor loading of a wrong indicator to 1. So say I measure neuroticism, but my first indicator happens to be simply a coin flip, then that is not a good indicator. Setting it to 1, then the factor loading will lead to very weird results in all the other factor loadings. The second identification rule is that we need positive degrees of freedom. The degrees of freedom are the difference between how many observations we have and how many parameters we wish to estimate. So A minus B, A is the number of observations, B is the number of parameters. We are fitting our model to the variance covariance structure. Right, so in this expression here, S is our observed information and the elements of sigma, which are in this expression, are our unobserved information or parameters we wish to estimate. That means that we need at least as much observations than the amount of parameters we wish to estimate. Now in the case of a variance covariance structure, our amount of observations is P, the number of variables, times P plus 1 divided by 2. And this will give you the amount of unique variances and covariances. So a variance covariance matrix is a square matrix. It has P times P elements, but the upper triangle is identical to the lower triangle. So it's a bit less than P times P. In general, we will need 3 indicators for a single latent variable model, or 2 for each vector when we have multiple correlated latent variables. Alright? Usually we can form our measurement model in these very nice path diagrams, which are very clear and a nice way of summarizing our model. So in this case we have one latent variable, eta1. It causes one observed variable, y1, which is also caused by residual error, epsilon1. I set the vector loading to 1 to scale the latent variable, but now I can see that I still don't have an identified model. So I have 2 pieces of information, or 1 piece of information, namely only the variance of y, and I have 2 parameters, psi ii, the variance of the latent variable, and theta ii, the variance of the residual. So in this expression for sigma, I can see that I have one element, and I want to equate sigma to s, so we could also put sii here. So I have one variance, but I have 2 parameters. So I can set psi ii here to anything, like 10 or 100, and then I can simply set theta to anything else to correspond to what I set psi to, and then I can get any result here. So I cannot estimate this. I cannot estimate both psi and theta from only one piece of information. If I have 2 indicators, I set here the first vector loading to 1 again. This one is set to be freely estimatable. Now I still don't have an identified model, because I have 3 pieces of information, the variance of y1, the variance of y2, and the covariance. But I have 4 parameters, 1 vector loading, 1 vector variance, and 2 residual variances. So that's a degree of freedom of -1, and that's not identified. One thing you could do here is set this vector loading to 1 as well, but then this psi1 will simply equate to the covariance between these 2 variables, and that's not that interesting to look at, or we don't need SEM for that, or confirmatory vector analysis. Now I have 3 indicators, and now I do have an identified model. I have 1, 2, 3, 4, 5, 6 parameters, 3 residual variances, 2 vector loadings, and 1 latent variance. And I also have 6 pieces of observed information. 1, 2, 3 variances, and 1, 2, 3 covariances. So my degrees of freedom is 0. That means that my model is identified, but it's saturated. So it's exactly identified, which means that I can perfectly reproduce any covariance structure using these parameters. So it's identified, it's not that interesting, because I will see it fits, but that's because it's exactly or saturated, so it will always perfectly reproduce my covariance structure. But now we get into a more interesting case where we can expand this and we can make it as big as we want. We can make these matrices as big as we want. And every time we just specify these matrices and we count the number of parameters and see if they have degrees of freedom above 0, sorry. So here I have 2 vectors, say neuroticism and extroversion. They're correlated, so there's a covariance matrix here. They have a variance. I set 2 vector loadings to 1 because I need to scale every latent variable in my model. And they have residuals. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 parameters. I have 6 observed variables, so that means I have 6 times 7 divided by 2 observations. I can also take this theta matrix here, which is the same dimensions as my observed variance covariance matrix, and count the elements. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 pieces of information, 13 parameters. So my degrees of freedom is 21 minus 13. that is 8, I think. It's at least higher than 0, which means my model is identified, and I will not exactly reproduce my variance coverage matrix, but that's good, because then we can do tests to see if the deviance from my model implied variance coverage matrix is due to chance or not. We'll come back to that next week. Now I can expand this. So for example, maybe the model doesn't fit between y3 and y4. Maybe these correlate in our observed variance coverage matrix much stronger than we would expect given our model. We can add a residual correlation. So here I added an extra model parameter. I can also add a cross-loading. So here I added a variance here. These are different from each other. So this model will allow y4 to correlate with y1, y2, and y3 more. This model will only allow y3 and y4 to correlate with each other more. And we can test that and compare them, and we'll come back to that next week. So that's really all there is to it. Confirmatory vector modeling means that we take these matrices, we fill them in, we form sigma, then we see if our sigma resembles S. Now in the software you usually don't need to do this. In some old software you need to specify these matrices with Greek letters. And also I'm writing an R package that has that kind of input. But the main software we'll use, like Lavaan or Onyx, it's much simpler. In Onyx we can simply draw this and fit the model. In Lavaan we can use expressions like in R for LM, for example, formulas to derive the model. So usually you don't need to do this, but it's very useful still to think in terms of these matrices, because it allows you to see what's really happening and to understand it. Alright, that's it. I'll see you all in the lecture.